Imagine you are working with a probability distribution. Maybe it describes how a disease spreads, or what a neural network believes about some data. You want to draw samples from it, simple enough, right? Here's the catch. Many distributions we actually care about cannot be normalized. The integral you need is intractable. It blows up in high dimensions. Standard sampling methods break down completely. MCMC is the workaround. Instead of sampling directly, you design a random process that wanders through the space and gradually settles into the right distribution. It only ever needs local evaluations. It never needs the normalizing constant. And yet, over time, its samples faithfully represent the full distribution. The name blends two ideas: Monte Carlo simulation and Markov chains. Each one solves a different piece of the puzzle. Let us take them one at a time. Monte Carlo. The name comes from a casino in Monaco where everything runs on chance. That is exactly the spirit of this method. Use random sampling to estimate things that would otherwise need a hard integral. The clearest example is estimating the number pi. Take a square with side length 2, its area is 2 squared, which is 4. Now inscribe a circle of radius 1 inside it. Its area is pi times r squared, and with r equal to 1, that is simply pi. So the ratio of the two areas is pi over 4, and that is our key formula. Now scatter points at random inside the square. The fraction that land inside the circle equals that same ratio. Multiply by 4, and you have your estimate of pi. Throw in more points, and the estimate tightens. The key insight is that random sampling replaced integration entirely. That principle extends to any quantity, any distribution. The catch is it demands independent samples, something many real problems cannot supply. That limitation is precisely what brings in the second ingredient. A Markov chain is a random sequence of states governed by a fixed set of transition rules, where the probability of moving to the next state depends only on where the chain currently sits, not on the path it took to get there. The chain is memoryless. Formally, the probability of the next state given the entire past equals the probability given only the current state. To make this concrete, imagine a weather model with 3 states: rainy, cloudy, and sunny. From the rainy state, there is a 60% chance of transitioning to cloudy. From cloudy, the chain may drift towards sunny, and from sunny, it can return. The transitions follow fixed probabilities, and each step is determined entirely by the current state. Watching the chain hop from state to state according to these rules is the Markov property in action. Run a Markov chain long enough under mild regularity conditions, and the fraction of time it spends in each state begins to settle toward fixed values. This limiting behavior is called the stationary distribution. A stable probability profile, the chain maintains indefinitely, regardless of where it started. The key technical requirement is that the transition rule satisfies a balance condition with respect to the target distribution. When the chain is carefully designed to meet this condition, its stationary distribution coincides exactly with the target. This is the central mechanism MCMC exploits. We cannot draw independent samples from the target, but if we build a Markov chain whose long-run frequencies match it, then running that chain long enough gives us samples that behave as if they came from the target directly. The hard part is constructing such a chain. The Metropolis-Hastings algorithm shows exactly how to do it. The clearest use case for MCMC is Bayesian inference. Given observed data, Bayes' theorem connects 3 quantities. The prior encodes what we believe about the parameters before seeing any data. The likelihood measures how well a given parameter value explains the observations. Multiplying them gives the unnormalized posterior, or updated belief after accounting for the data. To normalize this into a proper distribution, we divide by the denominator, the evidence, which is the integral of the numerator over all possible parameter values. In a model with many parameters, that integral spans a space of enormous dimension and is computationally intractable to evaluate directly. This is the wall Bayesian inference runs into. MCMC enters precisely here. The algorithm only ever evaluates ratios of the unnormalized posterior, so the evidence cancels and is never computed at all. Metropolis-Hastings is a concrete recipe that answers the exact question Bayesian inference runs into. How do you sample from a posterior you cannot normalize? It builds a Markov chain whose stationary distribution matches any target we choose, including a posterior. We can only evaluate up to a constant. The procedure is surprisingly straightforward. 4 steps repeated indefinitely. Step 1. Initialize. Begin the chain at any parameter value in the space. The starting point does not need to be good. Pick something arbitrary and the chain will correct itself. Early samples taken near this starting position will sit in a low probability region of the target. That is expected. Those samples belong to the burning phase and will be discarded. What matters is that the chain eventually drifts toward the high-density region on its own. Step 2. Propose a candidate. From the current position, draw a new candidate value from a proposal distribution centered on the current point. A Gaussian with some width sigma is the standard choice. The width matters enormously. Too narrow, and the chain takes tiny steps and explores the space very slowly. Too wide, and most proposals land far out in the tails where the density is low and almost every move gets rejected. Step 3. Compute the acceptance ratio. This is the key insight of the whole algorithm. Form the ratio R, the unnormalized target evaluated at the proposed point divided by the unnormalized target at the current point. Because this is a ratio of the same function evaluated at two different places, the normalizing constant on the evidence appears in both numerator and denominator and cancels completely. We never need to compute it. Step 4. Accept or reject. If R exceeds 1, the proposed point has higher posterior density than the current position. The move is always accepted, the chain steps uphill. Occasionally, when R is less than 1, the proposed point sits at lower density than the current position. The chain accepts this downhill move with probability R. Occasionally, accepting downhill moves is precisely what allows the chain to escape local peaks and map the full shape of the distribution, not just climb to the nearest summit and stay there forever. A move to a much lower region gets a tiny acceptance probability. A move only slightly lower is accepted most of the time. That balance is what gives MCMC its power. Each accept-reject decision adds 1 point to a growing sequence of parameter values, and the acceptance probabilities are calibrated so the chain visits each region in proportion to its posterior density. Early in the run, the samples are discarded. They belong to the burn-in phase, during which the chain may still be drifting from its arbitrary starting point toward the high probability region of the target. Once the chain has mixed, the samples that follow are effectively draws from the posterior. From those samples, you can compute the mean of any parameter, credible intervals, tail probabilities, predictive distributions, or any other quantity of interest. None of these require knowing the normalizing constant. The chain asks only for local evaluations of the unnormalized posterior at each step, and in return it gives you everything about the global shape of the distribution. That trade is what makes MCMC indispensable.